2 centimeters, across 13 acres of stone. That is the margin within which the base of the Great Pyramid of Khufu remains level, even now, after 45 centuries of wind, heat, seismic tremor, and the slow, patient settling of the earth itself. Pause long enough to feel the scale of that statement. 2 centimeters across a square of roughly 230 meters on each side, a footprint large enough to swallow cathedrals, a platform bearing more than 6 million tons of limestone and granite. And yet its foundational plane deviates by no more than the thickness of a finger. We are accustomed to admiring the height, the vanished summit that once rose to nearly 147 meters, the gleaming casing stones that reflected desert sun like a blade. We speak of alignment to true north within a few arc minutes. We marvel at right angles approaching 1 part in 10,000. But none of that explains the stillness. Stillness is not aesthetic, it is structural. The Great Pyramid does not lean, it does not twist, it has not sunk conspicuously into one corner while lifting at another. Its internal chambers, though weathered and robbed, do not display catastrophic foundational fracture. The geometry, though battered by time, remains coherent. And that coherence is not a matter of stacking skill. It is a matter of contact with the earth. 6 million tons do not forgive uneven ground. They magnify it. Imagine placing a single sheet of paper beneath one corner of a heavy table. The imbalance is subtle, almost trivial. Now scale that imbalance across a mass weighing millions of tons. What begins as millimeters at the base becomes measurable deviation in height. Angular error accumulates upward. Compression redistributes unpredictably. Stone that was meant to bear weight evenly begins to concentrate stress along unintended lines. In such a structure, the enemy is not gravity alone. It is differential settlement. The Great Pyramid stands upon the limestone bedrock of the Giza Plateau. That plateau is not a natural plinth carved by Providence in anticipation of a monument. It is layered Eocene limestone, stratified, fractured, weathered. The rock rises and falls in subtle undulations across what would become the pyramid's footprint. Bedding planes vary in density. Micro fissures thread through the stone. Some layers are harder, others more friable. Left untouched, such geology is unpredictable under load. If one corner of the pyramid had rested upon slightly weaker strata than another, settlement would not have been uniform. One edge might sink imperceptibly more over decades, another might resist. The consequence would not be dramatic collapse, but slow distortion, the quiet betrayal of geometry over time. Yet the pyramid does not display such betrayal, which leads us to a simple but unsettling conclusion. The ground was not accepted as found. It was altered. Modern surveys, including the meticulous 19th century measurements of Flinders Petrie and later geological mapping by researchers working on the Giza Plateau, reveal that the pyramid was constructed directly upon prepared bedrock, not sand, not compacted fill, carved limestone. The natural surface was cut down where it rose too high. Depressions were corrected. The builders did not merely clear debris, they reshaped the plateau into a plane. And that plane is astonishingly precise. To appreciate the magnitude of that achievement, consider contemporary construction tolerances. Modern concrete slabs for large industrial facilities may aim for flatness within a few millimeters over several meters, but across 230 meters, achieving uniform level within 2 centimeters demands laser instrumentation, optical levels, continuous calibration, and heavy machinery. Even then, engineers fight creep, thermal expansion, tool error, and survey drift. Now remove electricity, remove steel, remove digital measurement. Replace them with stone tools, copper implements, cords, sighting rods, human vision, and the physics available to anyone willing to observe it. The comparison is not romantic. It is uncomfortable, because it suggests that the foundational plane of the Great Pyramid was not approximate, it was controlled. There is persuasive evidence that shallow trenches were cut around the intended perimeter and filled with water. Water establishes its own horizon. It does not slope by opinion. It does not exaggerate or minimize error. It simply rests at level. If you carve a channel encircling a massive square and flood it, any point of rock protruding above that horizontal reference becomes visible against the still surface. Workers can then remove high spots until the stone conforms to the waterline. The method is slow. It requires patience. It requires repeated verification. But it is precise. Physics becomes instrument, and once a reference plane exists, every subsequent stone course depends upon it. The visible perfection of the pyramid, its straight edges, its symmetry, its stable ascent, is an expression of something that cannot be seen once construction begins. A disciplined surface that refuses to deviate. Here is the tension. The upper courses of the pyramid are dramatic. They rise toward the sky. They speak of ambition, of celestial alignment, of power. But none of that would matter if the base beneath them were even modestly unstable. If the foundational plane had been off by more than a few centimeters, the error would not simply remain at the base. It would tilt the entire structure. The alignment to cardinal directions would skew. The casing stones would not meet cleanly at the edges. The corners would fail to maintain right angles under compression. Precision above is impossible without precision below. And so the true engineering feat of the Great Pyramid may not be the raising of blocks to staggering heights. It may be the quiet, relentless act of disciplining the earth. Consider the psychological dimension of that labor. Before a single visible course was laid, there would have been months, perhaps longer, of work that produced nothing monumental to the eye. No rising walls, no ascending mass, only rock being shaved, inspected, corrected, over and over. The builders were not yet constructing a symbol. They were constructing a reference. This is not the glamorous part of architecture. It is the part that modern observers rarely imagine. Yet without it, the spectacle never materializes. And the statistics refuse to soften. Level within roughly 2 centimeters across 13 acres. Side lengths differing by less than 20 centimeters over 230 meters. Corners forming near-perfect right angles. Such figures are not compatible with casual groundwork. They imply process control, they imply remeasurement. They imply a culture unwilling to tolerate creeping error. We often ask how ancient Egyptians lifted heavy stones. A more penetrating question might be how they persuaded geology to comply. Because weight is honest. It reveals weakness without mercy. If the plateau beneath Khufu had been even modestly compromised, 6 million tons would have announced that fact across centuries. Instead, the monument remains composed. Its stillness is not passive. It is evidence. Evidence that before the first block rose toward the desert sky, something deeper had already been achieved. Something that required foresight, patience, and an understanding that geometry cannot float on uncertainty. So we arrive at a moment of quiet significance. The pyramid's perfection above ground is not the beginning of the story. It is the consequence. Beneath it lies a decision to reshape natural rock into a calibrated plane, to establish a standard against which all subsequent work would be judged, to ensure that the earth itself would not distort intention. And this leaves us with a final unsettling thought. If such care was required before the visible monument could exist, what else had to be established, socially, intellectually, structurally, before the first stone ever touched that leveled bedrock? What foundation, unseen and undocumented, made this discipline possible? The stillness of the pyramid is not silence. It is a question waiting beneath 6 million tons of stone. Stand upon the Giza Plateau at dawn, before the tour buses arrive, and the illusion is almost convincing. The desert appears level. The horizon runs clean and uninterrupted. The Great Pyramid of Khufu rises from what seems at first glance a natural stone terrace, a ready-made foundation awaiting its monument. But the plateau is not flat. It never was. Beneath the pyramid lies Eocene limestone, formed roughly 50 million years ago when this land was submerged beneath a shallow sea. Layer upon layer of marine sediment hardened into rock, each stratum preserving subtle differences in density, grain, and cohesion. Some beds are compact and durable, others are softer, more fractured, more vulnerable to stress. Geology is rarely uniform. It is a memory of time. Across the pyramid's footprint, some 230 meters per side, the bedrock undulates. It rises gently in places, dips in others. Natural fissures thread through the limestone. Bedding planes tilt imperceptibly. Hairline fractures, invisible to the casual observer, divide the rock into zones of slightly different strength. To the eye, these variations are trivial. To 6 million tons, they are decisive. When weight descends upon stone, it does not distribute itself abstractly. It seeks resistance. It compresses where the rock is weaker. It transfers load toward stronger zones. And if one region yields even slightly more than its neighbor, the result is not immediate catastrophe. It is distortion. This is the true adversary, differential settlement. Imagine a perfectly rigid block placed upon ground that compresses unevenly. One corner sinks a millimeter more than the others. That is all. A millimeter, less than the thickness of a coin. Insignificant. Not when multiplied by height. The Great Pyramid once stood nearly 147 meters tall. A 1 millimeter discrepancy at the base does not remain 1 millimeter at the summit. It translates into angular deviation. The entire structure tilts imperceptibly, altering the alignment of courses above. Compression redistributes unevenly. Stones meant to share load equally begin to carry unequal burdens. Now increase the error slightly, 2 millimeters, 3. Over decades under sustained load, minor disparities in bedrock density become amplified by mass. Stress accumulates along unintended vectors. Microfractures propagate. Corners cease to be exact. Edges drift. Geometry degrades. And once geometry degrades at scale, correction is impossible. The pyramid does not forgive foundational error, it preserves it. The Giza Plateau, composed primarily of the Mokattam Formation limestone, presents precisely this challenge. Geological surveys reveal that its surface before modification was neither smooth nor level. It bore the marks of ancient erosion, quarrying natural slope toward the Nile Valley. Some areas contained harder limestone suitable for casing stones. Others were softer and more fractured. To build upon such terrain without preparation would be to gamble the integrity of the entire monument. But let us quantify the threat more concretely. Consider a simplified model. If one corner of the pyramid's base were higher than the opposite corner by just 1 millimeter over a span of 230 meters, the resulting angular deviation would be small, yet measurable. Extend that angle upward across nearly 147 meters of height, and the lateral displacement at the apex becomes several centimeters. That is from 1 millimeter. 3 millimeters at the base could yield nearly 10 centimeters of horizontal deviation at the summit. 10 centimeters is not cosmetic, it is visible. It alters the intersection of faces. It disturbs the meeting of casing stones. It compromises the intended slope angle. It betrays the design, and this assumes static error. Add to that the slow compaction of weaker limestone beneath heavier load zones. Suppose one quadrant of the plateau contains slightly more fractured bedding planes. Under pressure, it compresses more readily. Over years, settlement accumulates not evenly but locally. The pyramid would not collapse. It would deform. Its internal chambers would experience stress redistribution. Corbelled ceilings might crack along unintended lines. Passages would shift by millimeters that compound over distance. We do not observe such systemic distortion, which means the builders faced this geological reality and refused to accept it as fate. The plateau slopes gently from southwest to northeast. Natural variations in elevation span more than trivial margins across the pyramid's footprint. There are bedding planes dipping at subtle angles. There are joints formed by tectonic stress long before human hands arrived. To ignore these conditions would have been easier. To conform the monument to the terrain would have required less labor. Many ancient structures did precisely that, adapting to slope, accommodating irregularity, accepting compromise. But the Great Pyramid does not adapt. It imposes. Its sides run straight and true as though drawn upon an abstract plane, not draped over uneven rock. Its base is level not by coincidence, but by intervention. This is the turning point. The builders confronted a geological adversary more patient than any human force. Limestone does not negotiate. It responds only to pressure and removal. It carries within it the memory of ancient seas and tectonic tension. And yet they decided the plateau would not dictate the geometry. Geometry would dictate the plateau. That decision is profound. It signals an understanding, whether formalized in theory or embedded in practice, that mass magnifies imperfection. That height amplifies error. That ambition without preparation collapses into distortion. 6 million tons act as an amplifier of truth. They reveal weakness, they expose asymmetry, they punish approximation. The pyramid stands as evidence that the amplification did not expose fatal flaws. Therefore, the flaws were addressed. Before the first visible course rose, the builders had to confront every irregularity across 13 acres of rock. They had to identify high points and reduce them. They had to compensate for depressions. They had to ensure that bedding planes of differing density would not introduce uneven compression under load. They could not rely on appearance. The plateau might look flat beneath the desert sun, but sight deceives across long distances. Human vision cannot reliably detect a millimeter deviation over 200 meters. They needed a reference that transcended perception, and that implies intent, sustained, disciplined intent. Here is the uncomfortable implication. The Great Pyramid is often framed as a monument of audacity, an act of scale so extreme it borders on obsession. But audacity without restraint is chaos. The greater the mass, the narrower the margin for error. To lift stone skyward is dramatic. To prepare ground so thoroughly that it never betrays the weight above, that is quiet, almost invisible work. Yet it is the more difficult challenge. For the plateau was not empty desert, it was layered time, fractured, tilted, subtly unstable in its natural state. The adversary was beneath their feet, and they did not ignore it, and they studied it, they cut into it, they disciplined it, which leaves us at a moment of tension that deepens rather than resolves. If the Giza Plateau was inherently uneven, if its limestone layers were fractured and subtly sloped, and if even a millimeter of uncorrected error could compound into visible deviation at the summit, then what exactly did they do to the Earth before daring to place the first block upon it? How did they transform unpredictable geology into a plane capable of supporting near-perfect geometry for 45 centuries? The answer lies not above ground, but carved into the stone itself, where the desert was forced into obedience. There is a moment in every great undertaking when intention ceases to be abstract. A line drawn in dust becomes a cut in stone. At Giza, that moment arrived not when the first limestone block was set, but when tools first bit into the plateau itself. They did not bend the design to the terrain, they bent the terrain to the design. Long before the visible mass of the Great Pyramid of Khufu rose against the sky, the surface beneath it was stripped, cut, and disciplined. Archaeological surveys and geological mapping of the pyramid's footprint reveal unmistakable signs of human intervention in the bedrock. Chisel marks, cut channels, shaved shelves of limestone where natural rises once stood. The Giza Plateau was not a convenient table of stone awaiting a monument. It was a rough, stratified expanse of Eocene limestone, rising and dipping across what would become a 13-acre square. Left untouched, those variations would have dictated compromise. Walls slightly out of true, angles adjusted to suit slope, a monument conforming politely to the earth. Instead, the earth was compelled to conform to geometry. In some areas beneath the pyramid's base, protruding limestone was cut down to meet a predetermined level. In others, depressions were filled or trimmed to match a common plane. The evidence is not speculative. It is visible in the exposed bedrock around the base and in the documented surveys conducted over more than a century. The surface we see today at the pyramid's edges is not entirely natural. It is curated geology. Imagine the scale of that act. 230 meters per side, more than 5 hectares of rock. Not soil that can be shoveled or sand that can be raked flat, but limestone that must be chipped, dressed, shaved with persistent labor. There were no hydraulic excavators, no rotary cutters, no diesel engines to grind through resistant strata. Only copper tools, stone pounders, human endurance. And yet the outcome, measured thousands of years later, remains level within roughly 2 centimeters across the entire base. To achieve that result, the builders first had to decide that natural irregularity was unacceptable. That decision marks a threshold. Many ancient structures are impressive in scale yet forgiving in their foundations. They accommodate slope. They settle into terrain. They accept the slight distortions imposed by uneven ground. The Great Pyramid does not. Its base is not draped across the plateau like fabric over stone. It is imposed like a rule. Survey data indicate that portions of the natural bedrock were quarried down by as much as several tens of centimeters to create a uniform surface. Quarry scars beneath the footprint suggest that the plateau was actively reshaped, not merely cleared. The builders identified high points and removed them. They did not average them out by piling stone above. They eliminated the discrepancy at its source. Visualize it. Methodically shaving rock from protrusions, hammering and chiseling away uneven rises. Stone dust settling in the dry air. The sun arcing overhead while nothing visible rises yet toward the sky. For months, perhaps longer, the work produces no monument, no vertical drama, only a plane, and this plane had to be consistent not locally but globally across the footprint. A slight misjudgment in one quadrant could not be compensated later by skillful masonry. Once the first course was laid, the foundational surface would define every subsequent measurement. The leveling of 13 acres without modern instruments strains the imagination. Today, engineers use laser levels projecting coherent beams across construction sites. They rely on digital sensors calibrated to fractions of a millimeter. Even then, they cross-check and recalibrate continuously to prevent drift. Now remove all of that. You stand upon uneven limestone extending farther than the eye can comfortably judge. The human eye is not reliable over 230 meters. A surface that appears level may deviate by centimeters, undetectable without instrumentation. So what did they use? The most persuasive hypothesis centers on a simple, inexorable principle. Water seeks its own level. Evidence from the plateau suggests that shallow trenches were cut along the intended perimeter of the pyramid's base. These channels could have been filled with water, creating a horizontal datum that does not depend on guesswork or visual estimation. Water does not lie. If a channel encircles the footprint and is flooded, any point of rock rising above that horizontal reference becomes immediately apparent. Workers can then remove the excess stone until the surface aligns with the water line. The method is slow, but its authority is absolute. Picture it carefully. A rectangular trench outlining the future pyramid, perhaps only a short depth carved into limestone. Water carried from nearby sources and poured into the channel. The surface settling into stillness. A line drawn not by string or shadow, but by gravity itself. From that line, measurements radiate inward. High points are shaved, low points adjusted. The plane expands from perimeter toward center, verified repeatedly against the unarguable horizon of water. No lasers, no optical levels, only physics. If you find yourself picturing modern survey crews with tripod-mounted instruments and blinking red beams, remember, the ancients had access to the same gravity that we do. They understood that water offers a horizontal reference independent of human bias. And once established, that reference becomes the arbiter of correction. There is another revealing detail. At the center of the pyramid's footprint, A natural bedrock knoll was left partially intact. Rather than quarrying the entire area flat, the builders integrated this central rise into the structure's core. That decision introduces complexity. If the surrounding plateau is cut down to a specific level, the central knoll must either be reduced to match or carefully measured relative to the artificial plane. It cannot remain an uncontrolled protrusion. Its height must harmonize with the surrounding surface. This implies that leveling was not merely peripheral. It extended across the entire footprint, accounting for natural variation and integrating it into a unified foundation. The result is not simply a flattened field of stone, it is an engineered interface between monument and geology. Here lies the deeper significance. They did not accept terrain as constraint, yet they redefined it as material. The plateau ceased to be background and became component. But even this invites a further question, one that intensifies as we consider the scale involved. To level 13 acres within 2 centimeters is a feat even today requiring rigorous verification. Over such a distance, a minor misreading at one end can propagate into measurable deviation at the other. How did they ensure consistency across 230 meters? How did they prevent cumulative error from creeping in as work progressed from one quadrant to another? How do you measure level across a distance where the curvature of the Earth itself introduces subtle differences in sightlines and where human perception cannot reliably detect millimetric variation? Standing upon that artificial plane today, it is tempting to imagine that it simply emerged through persistence. But persistence without reference breeds drift. The Earth was carved, high points were shaved, an artificial plane was imposed upon ancient limestone. Yet the true challenge lies not merely in cutting stone, but in knowing when to stop cutting, in knowing that the surface has reached the intended level and not overshot or undershot it by imperceptible degrees. Without modern tools, what standard did they trust? What invariant reference guided their chisels? The plateau was altered, but by what measure was it judged complete? Before mathematics was written in symbols, it was written in behavior. And few behaviors are more faithful than water finding its own level. Stand beside a still pool at dawn. The surface reflects the sky not because it is polished, but because it is obedient. Gravity acts upon every droplet equally. No corner rises in defiance, no edge sags in preference. The surface becomes an expression of the Earth's pull, pure, impartial, exact. Now imagine carving a shallow channel around a square more than 230 meters on each side. Imagine flooding that channel. In an instant, the desert possesses a horizon. Not a guessed horizon, not a sighted approximation, a physical fact. This is the quiet genius that may have guided the builders of the Great Pyramid of Khufu. The leveling precision of the pyramid's base, within roughly 2 centimeters across 13 acres, demands an instrument. Not necessarily a device of metal or glass, but a reference that cannot drift with opinion. Water provides that reference. There is persuasive archaeological reasoning that perimeter trenches were cut into the limestone of the Giza Plateau around the intended footprint of the pyramid. These channels, shallow yet continuous, could have been filled with water to create a horizontal datum encircling the construction area. Water does not slope unless acted upon by force. It does not exaggerate error. It does not compress under minor variation. It rests where gravity demands. If the trench encircles the square, then any point of bedrock rising above the waterline is too high. Any point falling below may need to be raised or adjusted in relation to the established plane. In effect, the builders could transform geology into a measurable field. Visualize the scene carefully. A raw limestone expanse beneath the Egyptian sun, the perimeter marked and cut, workers carrying water perhaps in skins or ceramic vessels, pouring it steadily into the carved channel. The trench fills, the surface settles. Wind disturbs it briefly, then stillness returns. The entire footprint now has a visible, tangible standard. If you are accustomed to seeing modern construction sites with green laser lines sweeping across concrete forms, consider this. A trench of water is an ancient laser level, slower, quieter, but governed by the same physics. The comparison is not poetic exaggeration. A laser level projects a beam defined by internal calibration. Water defines a surface governed by gravity itself. Both establish horizontality. Both allow deviation to be detected and corrected. The difference is not principle, but technology. And here lies the deeper implication. The builders did not need to invent new physics. They needed only to trust the physics already present. Yet trust alone is insufficient. Water as instrument requires discipline. The trench must be continuous, not broken. The bedrock walls must be cut to consistent depth. The water must be replenished if evaporation lowers the surface. Wind must be accounted for. Disturbances must be allowed to settle before readings are taken. This is not casual work. It is ritualized precision. The leveling of 13 acres using water as reference would demand repeated verification. Workers would mark points where the rock surface met the waterline. High spots would be shaved, the trench refilled or rechecked, corrections made incrementally, and crucially, the reference must remain stable. If the trench wall itself were uneven, the water would reveal that flaw as well. The perimeter would become both instrument and subject, its integrity as vital as the surface it measures. This suggests something profound. Before the pyramid could rise, a temporary world had to be created in which measurement was sovereign, noise had to be minimized, approximation rejected, shortcuts forbidden. A culture of patience must have prevailed. The Great Pyramid's base did not emerge from a single act of cutting. It emerged from cycles of correction, a dialogue between stone and water. One must imagine surveyors walking the perimeter, eyes trained not on distant horizons, but on the thin, shimmering line where water met rock. They were not lifting blocks yet, they were calibrating the earth. The leveling plane is not merely a physical surface, it is a decision to subordinate material to reference. Without that decision, 6 million tons would have amplified error mercilessly. Consider again the numbers: 2 centimeters across 13 acres. In modern engineering terms, that tolerance across such an area would invite admiration even with contemporary tools. To achieve it with nothing but manual labor and physical reference implies sustained oversight. Water provides a horizontal line at a given moment, but construction does not end in a moment. The pyramid would take years to complete. Courses would rise, weight would accumulate, pressure would settle into the bedrock. The leveling plane must not only be created, it must be preserved. This introduces a more subtle tension. Water can reveal horizontality at a given time, but what prevents the underlying rock from shifting slightly under initial loads? What ensures that reference points remain constant as work progresses? The builders would need fixed benchmarks, points cut into stable rock that serve as enduring standards against which later measurements are checked. Perhaps marks were inscribed into bedrock at specific elevations. Perhaps cords were stretched repeatedly between reference points. Whatever the method, the discipline had to extend beyond the initial flooding of trenches. Water is honest. Humans are fallible. The interface between the two requires vigilance. One can almost feel the mental strain of such work. Each correction must be modest enough to avoid overshooting. Remove too much rock and you create a depression that must be compensated. Remove too little and the plane remains flawed. The process is iterative, slow, unforgiving, yet what emerges from it is a foundation capable of bearing enormous mass without visible distortion. If you imagine the pyramid as a triumph of vertical ambition, pause and reconsider. Its first triumph was horizontal. Before the first course rose skyward, the earth beneath it was compelled into compliance with gravity's own rule. The waterline became judge and mentor. It taught the stone where to yield. And once the plateau was disciplined into a plane, geometry above could proceed with confidence. But there is a quiet fragility embedded in this method. Water reveals level in an instant. It does not guarantee permanence. Leveling is a moment of truth, a snapshot of horizontality at the time of measurement. The pyramid would take decades to complete. As its weight accumulated, as seasons changed, as heat expanded stone and night cooled it again, how was that original plane safeguarded against subtle drift? How do you ensure that the reference established by water remains authoritative years later, when trenches are dry and courses are rising? Creating level is one act. Maintaining level over time is another. And it is there, in the preservation of reference, that the true test begins. Leveling the plateau was not an act of erasure, it was an act of selection. When the surface had been disciplined to a plane and the perimeter obeyed the waterline, one feature remained rising from the center, a natural knoll of limestone, older than the monument that would surround it. The builders could have removed it. They had already demonstrated the will to shave stone wherever geometry required it. Instead, they chose to leave it in place and build around it. This was not convenience, it was a decision. At the heart of the footprint of the Great Pyramid of Khufu, the bedrock rises several meters above the leveled surroundings. Today, within the descending passage and certain substructures, exposed limestone reveals that the monument does not sit entirely atop laid blocks. It grips the plateau itself. The pyramid is not merely resting on Giza, it incorporates Giza. Why preserve that central mass of rock? On the surface, the answer seems practical. Removing thousands of cubic meters of limestone would have required immense labor for no visible gain. Leaving the knoll intact meant less quarrying, less transport, less time spent pulverizing solid bedrock into fragments only to replace it with quarried blocks. Estimates suggest that integrating the central outcrop may have saved tens of thousands of tons of stone. Even a modest knoll, rising 3 to 5 meters across a significant central area, could account for many thousands of cubic meters. In a structure containing roughly 2.6 million cubic meters of material, that reduction is not trivial. It represents labor deferred, sledges unpulled, copper tools spared. But efficiency alone does not explain the choice. There is structural logic embedded in the decision. A natural bedrock core provides anchoring. Instead of resting entirely on laid masonry, the innermost mass of the pyramid bonds directly to the plateau. The weight of the upper courses does not distribute solely across placed blocks. It transfers in part into solid, unbroken limestone, continuous with the earth below. This is not unlike rooting a tree. A structure entirely composed of stacked elements relies on friction and compression. A structure tied into bedrock gains an additional kind of stability, geological continuity, yet the choice introduces complexity. A flat, uniformly leveled base presents one plane of reference. A protruding central knoll creates another. The builders now faced a dual-plane calibration challenge. The perimeter surface had been established with meticulous horizontality. The central rock mass had to be measured relative to that plane, not merely left as it stood. If the knoll rose too high, it would disrupt the geometry of internal passages and chambers. If too low, the benefit of anchoring would diminish. It could not remain a natural irregularity. It had to be integrated into a precise architectural scheme. This required careful trimming. The top of the knoll was shaped to align with the intended internal layout. Passages were cut directly through it. Walls met it cleanly. It became both obstacle and foundation, shaped but not obliterated. Imagine the calibration required. Surveyors standing on the leveled perimeter, measuring inward toward the central rise. They must translate the water-established datum across open ground, verifying that the knoll's height corresponds exactly to the intended structural layers. Remove too much rock from its crown, and the alignment of corridors shifts. Remove too little, and the first courses of stone will not seat evenly against it. The presence of the knoll means that leveling was not a one-dimensional task, completed at the edges and forgotten. It had to be reconciled with a three-dimensional feature at the center. This is the first structural trial. The builders were no longer merely imposing geometry onto a flat surface. They were negotiating between imposed plane and inherited mass, between the perfection of a measured horizon and the stubborn reality of ancient limestone formed millions of years earlier. And there were risks. Natural bedrock is not uniform. It contains fissures, bedding planes, variations in density. Integrating it into the core meant trusting its integrity. If fractures extended unpredictably, they could transmit stress differently than laid masonry. If hidden weaknesses existed, they would be sealed within the monument itself. Why accept that uncertainty? Perhaps because the benefits outweighed the risks. Solid bedrock does not shift the way individual blocks might. It cannot be displaced by minor settlement between courses. It resists differential compression. By tying the pyramid's center to the plateau, the builders may have reduced the likelihood of long-term sagging or rotational stress. There is also symbolism embedded in the act. To leave the knoll is to acknowledge the land, not merely conquer it. The pyramid does not float above Giza, it grows from it. The boundary between natural and constructed blurs. The monument becomes less an object placed upon the earth and more an extension of it. Yet symbolism would not have justified structural compromise. The alignment of the base still demanded fidelity to the established plane. The knoll summit had to harmonize precisely with the first courses of limestone blocks radiating outward. One can picture the moment when the first ring of blocks met the shaped bedrock core. Stone against stone, quarried against primordial. The joint had to be exact. Any gap would magnify upward through thousands of courses. Any misalignment would echo through corridors and chambers yet to be cut. This integration also alters how we understand the pyramid's mass. When we speak of 6 million tons, we often imagine that weight as entirely transported. Yet part of the monument's volume is older than human intention. It is the plateau itself drafted into service. The saved volume is significant. If even 10,000 to 20,000 cubic meters of bedrock were incorporated rather than replaced, that equates to roughly 25,000 to 50,000 tons of material left undisturbed, thousands of labor days spared, countless tool strikes avoided, efficiency not through reduction of ambition, but through intelligent acceptance of what the land already offered. Still, the decision binds the pyramid intimately to its foundation. It is no longer a detachable structure that could, in theory, be disassembled and relocated. Its core is geological. Remove it, and you remove part of the plateau. The monument and the earth beneath it are fused. That fusion raises a deeper question. If the pyramid is anchored into bedrock at its center and seated upon a leveled plane at its perimeter, how tightly is it bonded overall? Does it rest by gravity alone, or does its integration with the plateau create a more profound mechanical unity? We tend to imagine the pyramid as stacked weight pressing downward, but perhaps it is also interlocked, keyed into the earth not just by mass, but by continuity of stone. The leveling of the plateau created a perfect plane. The central knoll ensured that the monument would never be entirely separate from its origin. Stone shaped by human hands met stone shaped by geological time. The first structural trial was not whether blocks could be lifted, it was whether the monument could be made to grow from the land without surrendering precision. The base was level, the core was anchored. The pyramid had begun to fuse with the plateau, but gravity alone does not explain stability. The question lingers, quiet but insistent. Exactly how inseparable did they make it? When the first course of stone was finally brought forward, the work changed character. Up to that point, the labor had been subtractive. Rock was cut down, high places were humbled. The plateau was disciplined into a plane and reconciled with the central knoll. But the moment the first limestone blocks touched that prepared surface, subtraction gave way to contact. And contact is where commitment becomes irreversible. The interface between bedrock and first course is not dramatic to the eye. There are no soaring lines, no visible triumph. Yet mechanically, it is the most consequential joint in the entire structure. Every block above, every chamber, every relieving stone, every outer casing slab would ultimately transmit its weight through that thin boundary where shaped limestone met shaped limestone. The first stones could not simply rest on uneven ground and rely on mass to correct imperfections. Weight does not fix misalignment, it amplifies it. If a block bears more heavily on one edge than another, stress concentrates there. Microscopic irregularities become zones of pressure. Pressure becomes cracking. Cracking becomes weakness. So the surface beneath the first course had to be more than level. It had to be intimate. The prepared bedrock was smoothed carefully where outer casing stones would sit. The contact area needed to be continuous enough to distribute load evenly, yet not polished in a way that reduced friction. It is a delicate balance. Too rough and point loads emerge. Too smooth and lateral resistance diminishes. The builders were working without formal stress equations, but not without experience. They understood weight. They understood that stone under compression behaves differently than stone under tension. They knew that a broad, flat contact spreads force. A narrow ridge concentrates it. When the first course was set, its underside met the plateau across wide surfaces. The load from above would not descend as a narrow spike, but as a distributed field. Each block became part of a network, sharing pressure with its neighbors, passing force downward and slightly outward through friction and compression. Imagine 6 million tons rising gradually above this interface. The pressure at the base would eventually reach several tens of tons per square meter. Not enough to crush limestone, but enough that any irregularity would reveal itself over time. If one stone bore slightly more weight because of a tiny projection beneath it, that projection would experience higher stress. Under sufficient load, it could fracture or compress, redistributing weight suddenly to adjacent areas. That redistribution might be minor, or it might propagate. This is why the first course is not simply a starting line. It is a membrane between geology and architecture. The outer casing blocks demanded even greater care. Their precision defined the visible geometry of the pyramid. Beneath them, the bedrock had to be shaved to match their intended alignment. A deviation of a few millimeters at the base could echo upward across 146 meters of original height. Load transfer in a pyramid is not purely vertical. Because of the inward stepping of courses, weight is directed slightly toward the center as it descends. This inward component enhances stability, pressing stones together rather than outward. But that same geometry means that any imbalance at the base can introduce subtle rotational forces. Consider a hypothetical difference so small it seems trivial: 3 millimeters. If one corner of the base were to settle just 3 millimeters more than the others, less than the thickness of a fingernail, the geometry of the entire structure would respond. Across a base length of about 230 meters, a 3 millimeter differential introduces a slope of roughly 1 part in 76,000, nearly imperceptible at ground level. Internal passages, calibrated to precise internal passages, calibrated to precise angles, would deviate. Stress distribution along the lower courses would no longer be uniform. One quadrant would bear marginally greater compressive force. 3 millimeters seems harmless, yet stone under constant load does not forget imbalance. Over decades, centuries, millennia, minute differences accumulate consequences. Compression can cause slight creep. Blocks may adjust microscopically. Mortarless joints depend entirely on precise fit and gravity's even hand. The builders appear to have anticipated this. The remarkable survival of the structure suggests that the base was not merely level at the moment of construction, but uniformly supportive. Stress concentration was avoided not through brute mass alone, but through preparation. There is something almost tender about this phase of the work. After reshaping the plateau and integrating the central knoll, the act of placing the first course required patience rather than force. Each block had to seat fully. Workers would test stability, perhaps rocking slightly to feel for unevenness, shaving away minor protrusions beneath until the stone settled without wobble. Contact had to be complete, because once the second course was placed, correction became exponentially more difficult. By the time the structure reached even a fraction of its final height, adjusting the base would be impossible. This is the deepening commitment. The pyramid ceased to be a plan and became a weight-bearing reality. Every new layer increased the consequence of every decision made below. And still, the question lingers like a fine crack in stone. Even with meticulous leveling, even with careful smoothing and distributed load, what happens if time introduces its own subtle asymmetry? What if thermal expansion, minor subsurface variation, or unseen geological shifts cause one corner to settle slightly more than another?
3 millimeters is enough to shift alignment.
5 might begin to concentrate stress measurably. 10 could initiate visible cracking. The pyramid stands today because those thresholds were never meaningfully crossed. But as the courses rose and the mass accumulated year after year, the builders could not know the future with certainty. They could only trust their interface, the bond between first stone and bedrock, to behave as intended. Gravity would test it relentlessly.
And gravity is patient.
Gravity is patient, relentless, and indifferent. It does not negotiate. It does not pause. Every ton of stone presses downward without hesitation, and beneath it, the earth responds in silence. Over time, that response can become a threat, subtle yet inexorable, the quiet adversary of any monument that reaches for the sky. Even when a base appears perfectly level, the rock beneath it is not uniform. Limestone, though seemingly solid, varies in density, in bedding, in microscopic fractures. Some zones compact more readily under stress, others resist. These variations are minute, almost imperceptible, yet when multiplied across thousands of cubic meters of stone, they introduce what engineers call differential settlement, the uneven descent of portions of a structure under load. In modern terms, consider a skyscraper. Even with steel reinforcement and poured concrete, engineers calculate expected settlement over decades. Foundations are designed not merely to support weight, but to distribute it evenly to prevent tilting or uneven strain that could buckle walls or misalign critical systems. They monitor soil composition, water table levels, and compressibility. Even then, subtle adjustments or correction mechanisms are planned to accommodate what nature inevitably imposes. At Giza, there was no concrete, no steel beams, no modern soil surveys or hydraulic lifts. Only the plateau's natural limestone, some layers dense and resistant, others fractured and more compressible. The builders had to understand, empirically, observationally, with repeated trials, how 6 million tons would bear upon it over decades and centuries. Differential settlement is silent. It does not announce itself with drama. It accumulates invisibly, millimeter by millimeter, as micro-compressions adjust the underlying rock. At first, the effect is negligible. A block might tilt a fraction of a degree, a course might press slightly harder on one edge, but the force multiplies upward. A minor deviation at the base translates into misalignment above. Angles, faces, corridors, all can warp without intervention. Time itself becomes a structural adversary. Heat, night cooling, seasonal changes in humidity, even subtle tectonic shifts, all influence limestone behavior. A depression that did not exist during construction may appear decades later, an almost imperceptible bowing in the foundation. Gravity exploits every inconsistency, every weak point. This is why the survival of the Great Pyramid is extraordinary. The precision observed today, the level base, the true north alignment, the perfectly intersecting faces, is evidence of preparation so meticulous that it neutralized differential settlement before it could manifest. It is a silent victory against a relentless force. Every millimeter of alignment above ground required anticipation of millimeters below ground, over decades, over centuries. Even small errors could compound disastrously. If one corner of the pyramid were to sink more than its neighbor by just a few millimeters, the apex could shift laterally by several centimeters. Stress concentration could occur along internal chambers, threatening their integrity. Exterior faces could warp, disrupting the meeting of casing stones and altering angles critical to both structural stability and the monument's geometry. The builders had no modern sensors to monitor settlement. They relied on repeated measurements, controlled placement, careful selection of which bedrock to preserve and which to cut or shave. The central knoll, integrated into the core, likely served as a stable anchor, reducing potential movement at the heart of the structure. Surrounding courses were distributed over leveled, disciplined bedrock to prevent localized overloading. The effect is that the pyramid itself became a self-monitoring structure, mass pressed evenly where it needed to, friction between courses absorbed minor inconsistencies, and geometry resisted lateral drift.
When modern engineers compare the Giza Foundation to a contemporary skyscraper, the scale of the challenge becomes even more apparent. Today, a 70-story building may sit on piles driven tens of meters into bedrock. Engineers monitor settlement over years, compensating where necessary with post-tensioned cables or adjustable columns. At Giza, the pyramid sits directly on the plateau, without augmentation, yet shows no evidence of differential settlement, large enough to misalign its courses by more than a few centimeters, over 4,500 years.
Time itself was an enemy, but one that the builders anticipated and mitigated. The survival of the structure is a testament not to luck, but to knowledge encoded in labor, observation, and method. They could not prevent gravity. They could only respect it, accommodate it, and design with it as a constant presence. And yet, the pyramid above ground, the striking perfection of its faces and apex, is not simply a matter of horizontal level. Leveling solves only part of the challenge. To maintain the fidelity of angles and slopes, to ensure that each course aligns precisely with the intended plan, requires more than a flat base. The precision of geometry itself becomes critical. The angles between faces, the intersection at corners, the inclination of ramps and internal chambers, all must account for the underlying mass and its subtle behavior under pressure. The silent killer, gravity, never rests. It acts on every stone, every joint, every interface. And the pyramid's integrity is proof that every potential failure was foreseen and neutralized before a single course rose high enough to reveal error. Precision above ground demands precision below. The moment the first course made contact, the battle with settlement was already won or lost. And while we admire the soaring faces, the true triumph is hidden, etched into the limestone beneath. A victory over forces that operate unseen, patient, and unrelenting.
The question, unavoidable and persistent, emerges as one contemplates the next layers. If leveling and load distribution were mastered, how did the builders ensure that each ascending course maintained perfect angular fidelity? The pyramid's visible geometry hangs in delicate balance, dictated not only by the level of the base, but by the precision of every angle, every slope, throughout the entire structure. At the foundation of the Great Pyramid, precision was not simply a question of horizontal level. A base can be flat, but a flat square alone does not produce perfection. Geometry demands more. Angles must meet exactly, corners must align, sides must remain true over distances that stretch longer than 2 football fields. The margin for error is minuscule, and the margin for cumulative error is almost non-existent. Measurements conducted in the modern era confirm what generations of surveyors have marveled at. The corners of the pyramid deviate from a perfect right angle by only around 45 arc-seconds. The side lengths, extending roughly 230 meters, differ by less than 20 centimeters. To achieve this level of accuracy by chance is statistically staggering. If one attempted to place 4 points randomly on the desert floor and call the result a perfect square, the odds against success are astronomical. Yet this square was not the work of randomness. It was imposed, controlled, and verified by human intention, working hand in hand with physics itself.
The challenge begins at the corners. Any slight misplacement of a single point at the foundation propagates throughout the structure. A small angular error magnifies as the pyramid rises. By the time the monument reaches half its height, a deviation of a few arc minutes at the base can produce a horizontal offset of several meters at the apex. The implication is clear. To secure the apex with near imperceptible deviation, the base must be more than level. It must be geometrically exact. Surveyors today can detect these deviations with sophisticated instruments, but the ancient builders had none of these conveniences. They had no theodolites, no total stations, no laser theodolites projecting beams across hundreds of meters. What they did have was a deep understanding of observation, triangulation, and iterative correction, tools of the mind and body sharpened by practice and necessity. One critical concern is maintaining squareness during leveling. The four corners must not only lie on the same horizontal plane, they must form precise right angles. If one corner drifts even slightly while the perimeter is being leveled, the entire geometry is compromised. The distance between corners may remain correct, but the angle is wrong, producing a subtle skew that only becomes visible much later, after hundreds of courses have been laid. The builders had to ensure that each stage of leveling preserved both horizontal and angular integrity simultaneously. The perimeter trench filled with water, the waterline, offers a partial solution for horizontal leveling. But horizontality does not automatically ensure squareness. Additional techniques must have been employed to control the angles. Measurements from corner to corner, from midpoint to midpoint, repeated across quadrants, would allow the detection of deviation. Using cords or sighting rods fixed at known points, workers could form geometric triangles, comparing lengths and angles repeatedly until satisfaction was reached. This is an exercise in patience and discipline. One misstep, one cord left slack, one misread line, and the angular fidelity could falter. Every step builds upon the last. Each block placed is a test of previous work. Angular drift begins at the foundation, imperceptible in its initial stages, but cumulative over the thousands of courses that follow. Unlike a modern building with adjustable beams or expansion joints, the pyramid cannot be corrected from above. Any misalignment set at the base is carried upward, multiplied, and eventually locked in by gravity itself. The statistical improbability of this achievement is staggering. Consider that each corner could have been misplaced by a few centimeters during measurement. Factor in human error, temperature fluctuations, wind, slight subsurface compression, and cumulative error across hundreds of steps. Yet the corners of Khufu's pyramid remain astonishingly true. Modern researchers estimate the likelihood of achieving this exactitude purely by chance to be vanishingly small, on the order of 1 in millions. This precision is not an accident. It is a testament to rigorous methodology and sustained oversight. To maintain this control, the builders likely employed a combination of triangulation, repeated verification, and physical benchmarks cut into the bedrock. They could have set fixed points at each corner, elevated and carved into stone, providing reference markers against which to measure continually. As the leveling progressed, these benchmarks would serve as immutable anchors, preserving both level and angular fidelity. The iterative process would involve checking distances between corners, confirming diagonals, and adjusting the surface until each point satisfied the geometric requirements. Even with careful planning, the task remained fraught with risk. Minute errors at one corner could propagate unevenly, twisting the alignment of one side relative to the others. A misalignment of a few millimeters at the foundation could translate into misalignment across dozens of meters, and by the time the pyramid reaches a height of 146 meters, even an arc-second discrepancy could affect the visual and structural integrity. Every measurement, every adjustment, every shave of stone had to be considered in relation to the entire structure. The interplay between angle, distance, and load is subtle but unforgiving. Corners act as hinges in the invisible skeleton of the monument. Side lengths enforce the angles. Slight deviations redistribute stress. Geometry, level, and mass are intertwined. A failure in one dimension reverberates across the others. The first course, anchored to the leveled plateau, carries the weight not just of stone, but of precision itself. It is here, at the foundation, that the pyramid's intellectual triumph becomes clear. The ancient builders were not merely lifting blocks or quarrying stone. They were imposing an exacting framework upon the earth. The magnitude of their ambition required not only labor but foresight, an understanding that the visible perfection above could only exist if every invisible measurement below was controlled. The corners, the sides, the diagonals, these were not incidental. They were arbiters of success. One misaligned angle, one slight error, and the entire geometric integrity could falter. And yet, after more than 4 millennia, the Great Pyramid exhibits angular accuracy that modern surveyors still struggle to reproduce, even with instruments far beyond what the ancients possessed. Every line cut in the plateau, every perimeter trench filled with water, every chord stretched across limestone, every subtle adjustment of the bedrock. These were steps in a calculation that demanded both skill and reverence. The probability of such precision occurring by chance is almost zero. It was human ingenuity harnessed to the immutable laws of geometry and gravity. And yet, even after achieving level and angular fidelity, the work is not finished. Measurement must be maintained over time. The base is stable, but construction stretches across decades. The pyramid rises gradually, each course adding weight, each block testing the stability of the prior layer. How did the builders ensure that angles remained true as the weight accumulated? How did they prevent drift over years when stones settle imperceptibly, when temperature and seasonal variation apply their subtle influence, and when even a single misalignment could magnify upward into catastrophic deviation? The answer lies at the intersection of observation, repetition, and discipline. The interface between geometry and gravity had to be continually verified. The foundation was not static, it was dynamic, continually reconciled with the work above. The pyramid's geometry demanded constant vigilance, an unbroken chain of measurement that tied each moment of construction to an invisible, perfect baseline. The magnitude of that challenge, the need to preserve absolute angular precision across centuries and millions of tons of stone, is almost incomprehensible. And yet, here it stands. A testimony not to luck, but to mastery over measurement itself, and to a vision of stability that begins with the unseen lines cut into bedrock and extends skyward, course after course, toward the apex. In modern engineering, we take for granted the tools that allow measurement to be preserved: laser levels, steel tapes, calibrated instruments that can be checked against known standards and adjusted with precision. At Giza, none of this existed, and yet the Great Pyramid of Khufu displays tolerances so precise that it rivals modern constructions. How was this achieved? Not through invention alone, but through a culture of invariance, a civilization committed to process, discipline, and the relentless preservation of measurement across decades.
The first course was laid on leveled bedrock, anchored to the central knoll, corners squared, diagonals verified. But even this was only the first step. Any baseline is only as reliable as the methods used to maintain it. The ancient Egyptians faced challenges that would be familiar to any surveyor. Cords stretch under tension, rods warp with humidity or sun, marks fade or chip. Small deviations compound quickly. 1 millimeter lost here, 1 millimeter misread there, and the consequences ripple upward, magnified by every additional course of stone.
Consider a simple cord used to measure a straight line between 2 points. Pull too hard, and it stretches. Let it sag, and the line bows. Even if the cord is tensioned correctly, repeated use or environmental changes can subtly alter its length. Yet to achieve the base's precision of 2 centimeters across 13 acres, such inconsistencies had to be anticipated and corrected. Measurement had to be verified again and again. Every chord must be checked against the bedrock, against benchmark points, and against other chords. A single error left unchecked could distort the angles of a corner or the alignment of an entire side. Rods, too, presented challenges. Long wooden rods might be cut from palm or cedar, but no material is perfectly stable. Wood expands with moisture, shrinks with heat, bows with age. The Egyptians mitigated this by repeated verification cycles. They would measure, record, adjust, and remeasure. Benchmarks carved into bedrock were likely referenced not once but hundreds of times over the course of construction. Each repetition reinforced fidelity, reducing the chance that a single error could propagate through the pyramid. This was not a casual process. It required a culture that valued consistency above speed, accuracy above spectacle. The laborers and overseers were not merely executing orders, they were custodians of an abstract principle that measurement, once established, must not drift. Every block, every line, every angle depended upon it. The repetition, the verification, the attention to minute detail. This is what allowed the construction of a structure whose tolerances remain astonishing today. It is tempting to view the pyramid as a monument to a king, to grandeur, to eternity. But the evidence suggests another perspective. The visible perfection of the pyramid is inseparable from the invisible rigor beneath it. A culture capable of sustaining such discipline is itself a rare artifact. We might call it a measurement culture, a society in which process is sacred, and deviations are not merely corrected, but prevented through institutionalized habits of verification and recalibration. Process discipline is, in a sense, a lost technology, not the technology of copper chisels or sledges, but the technology of sustained collective precision. It is a technology encoded not in stone, but in behavior, in ritual, in expectation. It is the repeated checking of baselines, the respect for the integrity of reference points, the understanding that a small error at one end of a chord can echo across hundreds of meters and centuries. Imagine the rhythm of work on the plateau. Teams moving between benchmarks, inspecting chord lines, confirming rod lengths, checking angles. Measurements recorded, adjustments made, trenches refilled, surfaces corrected. Errors anticipated, caught, and neutralized before they could escalate. The pyramid becomes not just a construction, but a manifestation of disciplined observation, a monument to the act of sustaining measurement itself. Even more striking is that this culture had to operate over decades. Khufu's pyramid required years of labor, likely across multiple reigns of skilled workers. No individual could oversee the entire process. Standards had to be transmitted, methods taught, verification cycles institutionalized. Knowledge of tolerances and procedures became communal, embedded in the workforce, perpetuated across generations of artisans. Every block carried the imprint of this collective, disciplined cognition. It is within this lens that the pyramid's true character begins to emerge. Perhaps it is less a monument in the conventional sense and more a calibration device, a physical expression of a civilization's mastery over measurement and material. Its perfection is not just aesthetic, it is procedural. Each level, each course, each stone reflects a commitment to invariance, to the unbroken fidelity of process. The idea is unsettling in its implications. We are accustomed to equating monuments with symbolism, with grandeur or religious intent. Here, the grandeur lies in control itself, the control of angles, levels, alignments, and the immutable laws of physics. The pyramid becomes a record, not only of human labor, but of an institutionalized understanding that reality, once measured, must be preserved with unwavering consistency. And this is where the tension deepens. Preserving horizontality and squareness over time is one challenge. doing so while the monument rises, while thousands of tons accumulate, while natural forces act silently and incessantly, is another. The culture of invariance had to be absolute, or the visible perfection above would have failed to emerge at all. Yet even such a culture has limits. What happens when a single cord stretches beyond expectation? When a rod warps in the sun? When a subtle misalignment goes unnoticed for hours or days? The stakes are enormous. Each minor deviation, if left unchecked, threatens the integrity of the entire monument. Maintaining process control is not merely about precision, it is about survival, about ensuring that the physical expression of knowledge endures. The pyramid teaches that technology is not confined to tools or materials. Process itself is a form of technology, one that requires understanding, discipline, and continuous engagement. The true marvel of Khufu's pyramid may lie less in the stone and more in the culture that produced, maintained, and enforced its invisible standards. And so, as the first courses rise and the structure begins to assert itself in 3 dimensions, the question lingers, subtle yet profound. If the visible perfection of the pyramid is inseparable from the unseen discipline of its makers, then could the monument itself be read not merely as a tomb or a symbol, but as a testament to a civilization's mastery over process, precision, and the unforgiving laws of reality? At the heart of the Great Pyramid, the distinction between the monument and the earth beneath it begins to blur. The plateau is no longer a passive platform. It is an instrument, a calibrated surface designed not merely to bear weight, but to participate actively in the stability of the structure above. The limestone bedrock, disciplined, shaved, and leveled, does more than support. It becomes part of the system, a silent partner in the preservation of geometry and the distribution of immense forces. The first courses sit upon this surface with almost imperceptible intimacy. Each block is a messenger of load, transmitting force into the bedrock. The mass of the plateau itself absorbs, diffuses, and redistributes these forces, acting as a vast natural spring, rigid yet forgiving enough to neutralize minor inconsistencies in the stonework. Unlike modern foundations, which rely on pilings or concrete slabs to manage compression, the pyramid uses the geological memory of eons, the inherent stability of lithified sedimentary rock, to achieve what is effectively a self-leveling, self-correcting base. Compression is neither vertical nor uniform. As each course is laid, weight flows downward through a complex network of stones, converging toward the core and dispersing toward the corners. The plateau ensures that this network remains coherent. Variations in density, minor fractures, and natural contours of the limestone are accounted for consciously or through iterative trial, so that stress does not concentrate but spreads evenly. The earth itself, shaped and disciplined by the builders, becomes a distributed load-bearing structure, amplifying the resilience of the pyramid rather than diminishing it. This integration is subtle, almost invisible, yet it is critical. The plateau is more than a foundation, it is a tool. In modern engineering, we consider foundations instruments, carefully designed surfaces that allow buildings to withstand earthquakes, soil creep, and settling. At Giza, the builders did not construct a separate instrument. They co-opted one that had existed for millions of years, shaping it to exacting standards and then marrying it to their architecture. The pyramid and plateau together function as a single structural system, inseparable, symbiotic. By comparison, later pyramids illustrate what happens when such discipline is abandoned. At Maidum, for instance, the outer casing collapsed catastrophically. The cause is still debated, but structural analysis suggests insufficient attention to bedrock preparation, overambitious layering without a perfectly disciplined base, and perhaps a lack of integration with the natural geological features. The very foundation that had stabilized Khufu's pyramid was missing or compromised. The result is instructive. Without careful engagement with the earth beneath, weight becomes a liability, not a stabilizer. The Great Pyramid demonstrates that structural integrity is not a property of the stones alone. It is a property of the relationship between stones, geometry, and earth. The plateau absorbs irregularities, compensates for minor misalignments, and locks the system into stability. The knoll at the core, the carefully leveled perimeter, the smoothed contact surfaces, all are part of a single apparatus designed to resist the silent, persistent force of gravity over millennia. Even the subtle differences in limestone density become tools rather than hazards. Slightly softer stone compresses under load, distributing pressure to adjacent blocks. Harder sections resist overcompression. In this sense, the bedrock acts as a living instrument, reacting predictably under stress, shaping the monument's endurance. It is a marriage of human intention and geological history, one that produces not only stability, but precision at a scale that is almost incomprehensible. The pyramid, then, is not simply a structure built on Earth. It is a structure in conversation with the Earth. The forces of gravity, weight, and mass are not opposed, but harnessed. The plateau, disciplined to a plane and integrated with the core, ensures that every ton contributes to the monument's fidelity rather than undermining it. This is a level of sophistication rarely seen in human history, an understanding that the environment itself can be harnessed as a tool for precision. Yet this realization carries a sobering implication. Later pyramids, such as those at Dashur, do not replicate this level of discipline. Casings collapse, angles drift, and structures that should have endured show early failures. When the calibration of the foundation is less exact, when bedrock is ignored or inadequately prepared, the system becomes fragile. The lesson of Khufu is unmistakable. Structural success is not merely about lifting stone. It is about commanding the interface between human design and geological reality. In essence, the plateau transforms from passive bed into active instrument. It sets the conditions for alignment, absorbs and distributes force, and preserves angular integrity across thousands of tons of material. Each stone rests not just on stone, but upon a foundation of time itself, sculpted to respond predictably to pressure and load. The pyramid's visible perfection is inseparable from this invisible system, a testament to a civilization capable of seeing the Earth itself as part of its machinery. And as one contemplates the monument rising above the plateau, it becomes clear that this is no mere tomb. It is a demonstration of mastery over both material and environment, a lesson in precision that begins in the invisible depths of the bedrock and echoes through every course, every chamber, every perfectly aligned casing stone. The question, ever present, lingers in the silence between blocks. If the plateau itself can act as an instrument, a calibrated surface integral to the pyramid's survival, what consequences unfold when future builders fail to replicate this union of geology and architecture? The history of later pyramids offers glimpses, but the magnitude of Khufu's achievement, a structure inseparable from the earth beneath it, stands alone. After Khufu's pyramid, the story of Egyptian construction takes a subtle but telling turn. The foundations of later pyramids, while ambitious, betray the absence of something invisible yet indispensable. Precision declines, angles deviate, casings crack, corners fail to meet as they once did. It is as though the meticulous discipline that underpinned the Great Pyramid had been diluted, weakened, or forgotten, leaving successors to contend with forces they no longer fully controlled. The evidence is clear. At Medum, the outer casing collapsed, the underlying courses exposed. At Dashur, in the Bent Pyramid and the Red Pyramid, inclinations shift slightly, corners no longer meet at the razor-edge accuracy seen on Giza. The cause is not merely engineering arrogance or stone quality, it is the loss of process rigor, the erosion of baseline fidelity, the failure to preserve the invisible systems that guarantee visible perfection. A baseline, once established, is fragile. It is the invisible spine of any structure, a reference that orders mass and geometry alike. If it drifts even slightly, the consequences accumulate. Consider a difference of a few millimeters at the base. At ground level, it seems negligible. Yet as stone is added course by course, that deviation propagates, amplified by the pyramid's height. Angles shift, corners drift. Faces that should converge precisely begin to bow. Small imperfections compound, creating asymmetries that are irreversible once the structure exceeds a certain scale. The process demands vigilance. Horizontal leveling, angular verification, corner alignment, all must be continuously monitored. Khufu's builders understood this. They did not measure once and assume permanence. Every chord, every rod, every trench was rechecked, recalibrated, verified repeatedly, sometimes over decades as the pyramid rose. Each repetition preserved the baseline. Each course locked the previous layer into a network of forces that resisted drift. When that vigilance wanes, precision falters. Even the most careful leveling cannot withstand unchecked cumulative effects. Settling, temperature, minor subsurface shifts, these are forces always at work. Without sustained attention, even a millimeter of baseline loss can cascade. Diagonals deviate, side lengths no longer match, apexes shift. The visible geometry, the measure by which the world recognizes a pyramid as perfect, begins to unravel. This fragility is not simply a matter of stone and mortar, it is a metaphor. Baselines once lost are difficult to recover. Control over measurement reflects control over process, discipline, and the transmission of knowledge. When Khufu's successors reduced the rigor of verification, they did more than compromise structural integrity. They revealed that mastery is inseparable from continuous attention and that excellence requires a culture capable of sustaining invisible work over decades. The contrast is instructive. Khufu's plateau is disciplined, his bedrock an instrument. Later builders used the same landscape, but failed to integrate it with the same meticulous fidelity. The result is clear in the physical record: deviations in angles, slight irregularities in casing alignment, subtle but cumulative misplacement. These failures are not random. They are the echoes of lost process, the consequence of allowing baseline drift to go unchecked. The lesson is stark. Perfection above ground is inseparable from control below. Without continuous verification, without an institutionalized culture that preserves precision across time and labor, geometry itself becomes fragile. The monument may rise, but its fidelity is transient. Khufu's pyramid endures not because of stones alone, but because the control of measurement was maintained relentlessly. The baselines, once established, were defended. This raises a haunting question. Perhaps the true lost technology of the ancient Egyptians is not copper tools, sledges, or ramps. Perhaps it is something far more elusive: the ability to impose discipline upon process, to maintain invariance over decades, and to ensure that every line, every angle, every benchmark remains inviolate despite the slow, patient forces of time and gravity. Without this discipline, even a structure designed with genius becomes vulnerable. Geometry once compromised cannot be fully restored. A few millimeters here, a few arc-seconds there, and the cumulative error erodes the visual and structural integrity that had been so painstakingly achieved. The baseline is fragile, and the consequences of neglect are profound. Khufu's pyramid is a testament not only to technical skill, but to the relentless preservation of invisible standards. It demonstrates that survival at scale requires mastery not just of materials, but of process itself. Later pyramids remind us that without such mastery, ambition alone is insufficient. Structures crumble, angles drift, and the memory of precision fades. And so we are left with a provocative thought. If the visible monument is inseparable from the unseen discipline, then the greatest loss of all may not be a lack of tools, or manpower, or wealth, but the disappearance of control, the capacity to sustain absolute fidelity to a baseline that defines not just a building, but the very possibility of perfection.
The question lingers, sharp and persistent. If the true technology lies in control, then what does it mean for civilizations that lose it? How do the subtle failures of process echo through history, shaping not only monuments but the memory of human capability itself? For 4.5 millennia, the Great Pyramid has existed as both monument and experiment, silently proving the accuracy of every decision made at its foundation. Weight, in this case, is not merely mass. It is evidence, a continuous passive stress test that no human observer could replicate. Every stone presses downward, every course exerts force upon the one beneath it, and yet, despite the relentless pull of gravity, the structure remains stable, precise and upright. It has endured earthquakes that rattle the desert. Seismic events, both subtle and moderate, have passed through the Giza Plateau, yet the pyramid stands with its geometry essentially intact. Its corners remain aligned, its sides retain the intended inclination, and its apex maintains the theoretical position dictated by design. Where modern engineers might rely on sensors and reinforcements to detect and correct shifts, the Great Pyramid offers proof that thoughtful engagement with natural forces can substitute for artificial intervention. Erosion, too, has tested the monument. Wind, sand, and occasional rain have worn at the casing stones, yet the underlying structure absorbs and redistributes stress without catastrophic failure. What might have seemed an inevitable deterioration has instead been a long-term demonstration of resilience. Every surviving layer, every intact block, attests to the careful calibration of mass and angle at the moment of construction. The pyramid becomes, in essence, a physical record of force distribution over time, a lesson written in stone and gravity. Even the removal of its outer casing, the very polished Tura limestone that once reflected the sun across the desert, has not compromised structural integrity. The inner core, supported by the disciplined interface with the bedrock, bears the weight effortlessly, a silent vindication of design decisions made thousands of years ago. Where some might see only stripped grandeur, the truth is more profound. The structure functions as intended, regardless of cosmetic loss. Weight proves the principle, and time validates the method. Viewed this way, the pyramid is a long-duration physics experiment. The builders imposed a system of forces, angles, and mass onto the bedrock, and the Earth responded over centuries. The result is data, recorded not on paper, but in millimeters of preserved alignment, in the stability of corners, in the enduring true north orientation. Modern engineers conduct stress tests over months or years. Here, the test spans millennia. Every earthquake, every temperature cycle, every load redistribution serves as a new trial, and the structure continues to pass with near-perfect scores. Weight becomes a witness to precision. Where verification methods of the past were manual, human, and ephemeral, gravity acts continuously, unrelenting and unbiased. It does not forget, it does not forgive. Yet, in the case of the Great Pyramid, it confirms every design assumption, every leveling decision, every geometric calculation made on the plateau. The very mass of the structure functions as both challenge and measurement tool, proving that the interface between human intent and natural force can achieve extraordinary fidelity. Even more striking is the scale. 6 million tons of limestone press downward, yet each course and chamber maintains its alignment, proving that the invisible preparation beneath the surface, bedrock leveling, knoll integration, perimeter control, was not theoretical. It was real. It worked, and it continues to work. No modern engineering software, no calculated reinforcement, no intervention from humans is required. Time itself serves as the final arbiter, and the pyramid passes with unbroken precision. In this context, the structure teaches us something subtle but profound. Measurement, when properly anchored to the laws of physics and disciplined in execution, endures. It is not a momentary act. It is a continuous process, validated over centuries, verified by the forces that shape our world.
The Great Pyramid becomes an ongoing experiment in load distribution, stability, and the predictability of materials and geometry under sustained stress. And yet the lesson is not merely engineering, it is philosophical. The pyramid's survival demonstrates that foresight, discipline, and understanding of fundamental principles can create outcomes that transcend generations. It is a dialogue between human intention and natural law, a record of what happens when process and material converge with extraordinary precision. Even now, as we measure its corners and recalibrate our understanding of its angles, the pyramid speaks. It is still teaching, silently, continuously, and unerringly. Every ton of limestone, every degree of slope, every millimeter of settled bedrock is data, accumulated over centuries, affirming principles that modern civilization is only beginning to fully appreciate. The question arises, quietly but insistently. If this monument has survived every conceivable stress test for 4,500 years, what does it teach us about the fidelity of measurement, the discipline of construction, and the human capacity to impose lasting order upon a chaotic world? The answer may be more than architectural. It may be a meditation on permanence, control, and the interaction between knowledge and the forces that shape reality itself. Even today, in an era of steel, concrete, and digital measurement, the challenges faced by the builders of Khufu's pyramid echo across modern megaprojects. Skyscrapers, bridges, dams, all rely on precisely established baselines to maintain stability. Surveyors use water levels, laser instruments, and GPS technology to measure horizontal planes, angles, and elevations with millimeter accuracy. Foundations are poured with exacting specifications, often anchored deep into bedrock to resist settlement. Yet despite the sophistication of modern tools, the vulnerability of even the most advanced systems to drift is constant and unavoidable. Consider a contemporary high-rise. Engineers can calculate expected settlement in soil and design compensation systems to prevent tilt. Still, micro-movements occur. Differential settlement can cause stress concentrations, minor misalignments, and even structural failures if left unaddressed. Precision in measurement is no guarantee of permanence. It is an ongoing negotiation with forces that are always at work. The longer the structure, the taller it rises, and the more massive its materials, the more critical the baseline becomes. A deviation of a millimeter at the base may translate into centimeters at the upper stories, a discrepancy that can compromise both geometry and function. In technology, the same principle applies, though invisibly. Atomic clocks, GPS satellites, and global positioning systems provide reference frames for everything from navigation to telecommunications. Millimeters matter in orbit, as timing errors or drift can propagate into kilometers of positional inaccuracy on Earth. These systems, like the pyramid, are only as reliable as their baselines and their preservation. Without continual calibration, verification, and redundancy, the precision upon which entire societies depend could unravel. The comparison is striking. The Great Pyramid, built without lasers, sensors, or GPS, maintains its millimeter and arc-second tolerances over 4,500 years. Modern skyscrapers, despite their advanced instruments, can exhibit measurable differential settlement over decades. Bridges bend under cumulative stress, concrete dams crack and leak. Invariances that are assumed today must be actively maintained. In antiquity, they were engineered into the process itself, disciplined across generations of laborers. Khufu's monument becomes a reference point in itself. Its stability is a silent reminder that permanence is achieved not merely through materials, but through process. The continual verification of measurements, the anticipation of movement, and the integration of structure with the environment. The plateau, the knoll, the leveled bedrock, all serve as baseline instruments that hold the geometry of the pyramid, with a rigor modern engineers can only replicate with electronic feedback systems. Yet this dependency carries its own vulnerability. Modern civilization relies on invariant references every day: atomic clocks for timekeeping, satellites for location, standards for measurement. If these references drift, if verification fails, if calibration is neglected, the consequences ripple outward, much as a misaligned foundation affects every course above it in a pyramid. Precision, whether ancient or contemporary, is fragile. It requires sustained attention, oversight, and respect for the underlying laws that govern it. The lesson is unsettling. Across millennia, the same principle governs success. Invariant reference frames must be preserved, or systems fail. The difference is that Khufu's builders achieved this with no digital instruments, no sensor networks, no theoretical models. Yet their result endures with astonishing fidelity. Modern projects, despite all technological advantage, remain vulnerable to drift, settlement, and human error. We are forced to confront a paradox. Millimeter precision can be maintained across 4,500 years when the culture enforces discipline over generations. Yet in the modern world, where instruments provide instantaneous feedback, we still struggle to maintain invariance over decades. It is a sobering reminder that measurement is not a momentary act. It is a sustained process, a continuous negotiation with reality, whether in stone or in silicon. And so the question arises, pressing and uncomfortably familiar. What happens when reference systems weaken? When verification is neglected? When instruments drift? When process is abandoned in favor of convenience? The pyramid remains stable, a monument to rigor. Our modern structures are only as secure as the fidelity we enforce. The stakes are existential, whether measured in stone or in data, in meters of concrete or milliseconds of time. The comparison is humbling. A civilization that maintained baselines with nothing but cord, rod, and observation produced a structure whose millimeter tolerances endure. A civilization with atomic clocks and satellites struggles to prevent deviation over decades. Precision is not inherited, it is enacted, enforced, and protected. And if those protections fail, drift is inevitable. The silent warning emerges. Control over reference frames is the foundation of stability. Whether in ancient limestone or modern steel, in pyramids or GPS networks, the principle remains the same. Baselines are fragile. Precision is conditional, and civilizations that take them for granted may find their structures, their systems, and their understanding of the world subtly but inexorably compromised. The question hovers: if Khufu's pyramid still stands as the ultimate demonstration of sustained precision, what might our modern constructs reveal or conceal about our own ability to maintain invariance across the span of decades, centuries, or longer? Beneath the monumental stone courses of the Great Pyramid lies the true hero of its story, not the pharaoh for whom it was built, not the colossal blocks heaped in geometric perfection, but the invisible labor that shaped the earth itself. The visible pyramid, imposing, elegant, eternal, is a triumph, yes, but it is only the consequence of something far subtler, far more profound: the discipline imposed upon the bedrock. It is here, beneath the first course, where intention meets reality, where human foresight wrests control from chaos. The bedrock was not a passive stage awaiting construction. It was an active participant, disciplined into alignment with the builder's vision. Protrusions were shaved, depressions filled or leveled, and the natural knoll integrated into the core, not merely tolerated but harnessed. This invisible preparation dictated the success of every stone laid above it. The foundation was a living instrument, absorbing, redistributing, and reconciling forces in a way that a modern engineer would envy. The pyramid rests not on the desert, but on a carefully calibrated interface with the earth itself. This labor was meticulous, iterative, and unrelenting. Every cut into limestone, every smoothing of a surface, every measured distance carved into stone ensured that the first course, the anchor for 6 million tons, would not merely sit, but perform. Slight errors were not tolerated. They were caught, corrected, and disciplined out of the system. It is this invisible work that allows us to marvel at level tolerances of 2 centimeters across 13 acres, side length deviations under 20 centimeters, and corner angles accurate to 45 arc seconds. Without the hidden labor beneath, such precision above ground would be impossible. We often equate heroism with visibility, the towering pharaoh, the grand procession, the spectacle of colossal construction. Yet in Khufu's pyramid, the hero is invisible. It is the labor that cannot be seen, the measurement that cannot be touched, the verification that leaves no mark. The hero is the repeated checking of baselines, the preservation of geometry across decades, the anticipation of settlement and drift before a single block is lifted. The human mind, disciplined and methodical, transforms bedrock into an instrument capable of sustaining perfection. The earth itself is disciplined into compliance. Natural fractures, subtle slopes, density variations, all are accounted for, measured, and integrated. The plateau ceases to be simply a location and becomes a tool, a co-architect in a system that unites natural law and human intention. The pyramid above, with its perfect alignment, smooth casing, and unwavering geometry, is only the visible shadow of this invisible achievement. Reconsider the statistics that stunned surveyors. Level across 13 acres to within 2 centimeters, side lengths consistent within 20 centimeters, corners square to 45 arc seconds. These figures are no longer mere curiosities or examples of ancient ingenuity. They are evidence of a disciplined process, of continuous human oversight, of a culture capable of sustaining absolute fidelity to a baseline over decades. Each number now carries deeper meaning. It reflects the success of invisible labor shaping reality itself. This invisible hero also reframes our understanding of construction. The pyramid is no longer just a tomb or a symbol of divine authority. It is a demonstration of process mastery, a monument to discipline, and a record of human ability to integrate with, rather than merely exploit, the natural world. The stone blocks are dramatic, yes, but they are secondary. The foundation, the leveling, the calibration, these are the elements that define success, the quiet triumph upon which the visible world depends. And yet the story forces us to reflect on our own modern efforts. If we built today without stable baselines, without the discipline to maintain them, what would endure? Skyscrapers, bridges, and satellites rely on precisely the same principles: measurement, verification, and control over invisible variables. Without them, the visible achievements crumble, twist, or drift. The lesson from Khufu is stark and humbling. The endurance of a civilization's monuments depends less on size, spectacle, or material, and more on the invisible work that imposes order upon chaos. We have spent millennia marveling at the Great Pyramid's outer perfection, yet its true story lies beneath. The invisible hero, the disciplined interface with the earth, has borne the weight of time, force, and gravity, sustaining geometry that has confounded humans for centuries. Every course, every angle, every millimeter of tolerance is a testament not merely to skill, but to the quiet triumph of foresight and rigor. The pyramid stands today, 4,500 years later, as a reminder that true mastery is not always visible. It teaches us that durability, precision, and beauty emerge first in the unseen, in the carefully disciplined interactions between humans and the environment. The earth, when treated as an instrument rather than a passive stage, becomes part of the monument itself, ensuring that vision, once imposed, endures. And so we are left with the enduring question, now sharper than ever. If we were to build today without stable baselines, without the culture of verification and discipline that Khufu's builders exemplified, what would endure? The stone would remain, perhaps, but would it bear the weight of millennia? Would it resist time, gravity, and entropy with the same quiet, unyielding precision? The answer lies in the invisible hero, the silent labor that transforms earth into instrument and human intention into permanence. The final lesson of the Great Pyramid is subtle, almost imperceptible. It is not the story of colossal stones defying gravity, nor of human ambition reaching for the sky. Those narratives, dramatic though they are, miss the point. The true achievement lies elsewhere. It lies in constraint, in discipline, in the deliberate obedience to principle rather than impulse. The pyramid does not merely rise, it demonstrates the mastery of process, frozen and immutable. Every course of limestone, every angular decision, every millimeter of tolerance above and below ground is evidence of a civilization enforcing fidelity upon reality itself. The plane beneath the sky is what matters. The bedrock, shaved and leveled, integrated into the central knoll, disciplined through repeated verification and careful calibration, becomes more than foundation, it becomes reference. The plateau, once passive, is now active, a tool, a canvas, an instrument upon which the visible pyramid rests. The structure is not a monument of ambition, but a manifestation of constraint obeyed, of rules observed with unflinching rigor. In this, it transcends architecture and becomes philosophy in stone. Consider the consequences. A civilization that understood the power of a preserved baseline could achieve what seems impossible: millimeter precision across 13 acres, angular fidelity to 45 arcseconds, alignment with true north to within fractions of a degree. These are not feats of brute force, but of method. It is the enforcement of invisible order that allows visible perfection to emerge. The pyramid teaches that control, discipline, and repeated verification can triumph over the chaos of natural forces, over the relentless pull of gravity, over the erosion of time itself. This lesson extends far beyond Giza. Civilizations rise not by ambition alone, but by the discipline to measure, to verify, and to preserve standards across generations. The Great Pyramid is a lesson in stability, in endurance, in the invisible structures, intellectual, procedural, and geological, that support the visible world. The beauty, the height, the sheer spectacle are the consequence of mastery beneath the surface, of fidelity maintained over decades, and of a culture capable of sustaining this commitment. And yet, this teaching carries a warning. Every system, no matter how sophisticated, is only as strong as its baselines. If reference frames drift, if calibration falters, if discipline is abandoned, structures fail. History is littered with evidence. Later pyramids collapse, modern buildings tilt, bridges sag, and technologies drift from their intended positions. Stability depends on persistence, on the continuous enforcement of invisible rules. The pyramid reminds us that what survives is not necessarily what is largest or most ambitious, but what is disciplined, verified, and held in line with immutable principles. Now, when we look upon the Great Pyramid, we see it differently. Height is no longer the defining measure. Scale is no longer the story. Instead, we perceive a plane of reference, of control, of carefully preserved intention. The visible monument is the shadow of invisible work, of geological compliance, of measurement that endured through centuries. The majesty is not in the stones themselves, but in the network of constraints that allowed 6 million tons to sit in perfect harmony, untouched by time or nature. The plane beneath the sky is the real gift of Khufu's builders. It is both foundation and message, that permanence is not achieved through ambition alone, but through process, discipline, and the respect for the laws that govern both matter and measurement. The pyramid becomes a meditation on stability, on the consequences of drift, and on the human potential to impose enduring order upon the natural world. And finally, the philosophical question remains, haunting and open-ended. If our baselines drift, if the invisible structures we rely upon falter, what in our world will remain standing? The answer is not in grandeur or scale, but in the unseen discipline we cultivate, the invisible planes we shape, and the fidelity we preserve. Khufu's pyramid endures because the plane beneath it was disciplined, verified, and maintained with unyielding rigor. Perhaps in understanding this, we glimpse a path to building not only monuments but civilizations capable of surviving the passage of millennia. Thank you for joining us on this extraordinary journey through the universe on frontiers of infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us where we unravel the darkest mysteries of space.